Okay, I myself senior medical physicist in Akuh University Hospital, and the topic which I am going to cover is interaction of ionizing radiation and measurement of absorbed dose. Okay, this has to be here. Radiation interaction with matter. When the X-rays or gamma beam passes through a medium, interaction between photon and matter can be take place with the result that energy transferred to the medium. The initial step in the energy transfer involves the ejection of electrons from the atom of the absorbing medium. These high-speed electrons transfer the energy by producing ionizing excitation of the atom along their path. If the absorbing medium consists of a body tissue, sufficient energy may be deposited within the cell and destroying the reproductive capacity. However, most of the energy is converted into heat and producing no biological effect. So if we talk about the photons, the photon fluence can be presented by the fluence number of particle per unit area, number of particle passing through per unit area in the sphere of the cross-sectional area. The photon fluence rate can be defined with the help of this equation and energy fluence. And if we solve these equations, we will get the energy fluence is equals to number of photons incident per unit cross-sectional area multiplied by energy, where dn is the number of particle with energy. So for if you consider the monoenergetic beam, example cobalt 60, I think I have to open the chat box as well. Okay. Okay, where h nu, the energy carried by each photons. So energy fluence rate is given by fluence differential of fluence and per unit time. Now consider the photon interact with any medium or any attenuation, the medium which attenuate the photons. So process of attenuation represent the fraction of photons removed per unit thickness of material from the primary beam. So the detector is placed in such a way that it will not detect any scatter photon. Consider it as a monoenergetic beam. It interact with the material, and there is a scatter photons and transmitted photons, but they will not detect on the detector. So these are the ideal conditions were in this experiment. So the intensity of narrow monoenergetic photon beam attenuated by an observer for thickness can be defined with this equation, intensity in a form of intensity, where mu is a linear attenuation coefficient. With the considering this diagram, then we have a concepts of half value layer, mean free path, and 10th value layer. So half value layer is defined as an absorber thickness that attenuate the original intensity to 50%. So we have placed such a material that attenuate the beam around 50%. So it's considered to be half value layer. The concept is quite similar with the half life. And these are the formulas, and the 10th value layer is important for shielding calculation. Now, for example, half value layer of cobalt 60 is 11 cm in water. Hence, the mean free path, if you put the value in this formula, you can calculate that mean free path is around 60 cm for 1.25 MeV photon. The half value layer and the 10th value layer for polyenergetic beam, and you can see the diagram here, transmitted intensity and absorber thickness. Anything?
Sorry for your interruption. Could you please define the monoenergetic and polyoenergetic beam?
I can't hear you clearly.
Could you please define the polyoenergetic and monoenergetic beam?
Okay. Actually, the X-ray photon beams are the polyenergetic. For the derivation or making a simplification equation, we consider the beam to be monoenergetic. Is that okay?
Yes.
Normally,
What is the
X-rays
difference?
are polyenergetic. X-rays or gamma
Yes.
rays are polyenergetic. But for the
Yes.
theoretical concept, to understand the equations or to make the formulation, we consider the beam to be monoenergetic.
Yes.
Okay.
When you say the monoenergetic beam, it means each photon have the same amount energy.
Yes. Yes.
And polyenergetic beam, it means the photons carries different energies.
Yes. There is a spectrum of the beam.
Okay, that's good. Thank you.
Okay. The half value layer and the 10th value layer for polyenergetic beam. So this is the diagram which you can understand. The absorber thickness increase, the half value layer, the half value, the transmitted intensity decrease. So this is the 50% intensity decrease. So it's considered to be first half value layer, the second half value layer, and the third half value layer. And these concepts are important in shielding calculations. In the shielding material used for the radiation, like if you are making a blocks, or if you consider the MLC, the thickness of the MLC, how much the thickness of the MLC depending on the energy, and these half value layer will define that how much thickness you required for specific material. This diagram is specifically for aluminum. So for mega voltage beam, we usually define the first 10th value layer and equilibrium 10th value layer. These are the values. You can get these values in tables when you do the shielding calculation. The tables are provided by the IAEA and the booklet. So the typical value of 18x. Whenever the shielding calculation was done, we consider high energy, high available energy. So 18x. So primary barrier, 10th value layer is 45 cm concrete. But 10th value layer equivalent is 43 centimeter concrete. Secondary barrier. Primary barrier is defined as direct to the beam. The secondary barrier, the scatter radiation all around the beam. The secondary barrier considered. So primary barrier is at 90 degree of the gantry, or the 270 degree, or 0 and 180 degree. So these are the primary barrier. And the secondary barrier are all other angles are considered to be secondary barriers. So why there is a difference between the TVL1 and the TVL equivalent? So this is the reason.
Hi, sir.
Yes. Tell me.
I have a question, please.
Yes, you can
How
ask.
does calculation for the first 10 value layer? It means how calculation it is 45 centimeters for concrete.
There is a distortion in your voice. I don't get it what you are saying.
The method of calculation of this.
Can you write the question on the chat box? I will read, and because your voice is not clear.
Yes, I will do. Thank you.
I'm waiting. Okay, I'll continue, and once the chat box, I will get the question, I will answer it. For the broad beam,
Yes.
there are two competing effects: beam hardening and Compton scattering. So beam hardening increase the average beam energy and consequently increase the TVL with the depth, whereas the Compton scattering decrease the average beam energy. TVL reduce the 1/10 intensity. That's right. Is left. No, the first option is right. Well, Saif Abdul Hadi question is how does it calculation the value of first TVL one? So we are this is not our topic right now, so I'm not gonna commit right on this thing. It's a part of shielding calculation. So right now it's just a concept, not going into detail of the calculations. Is that okay, Saif?
Okay, okay, thank you.
Okay,
Thank you.
okay. So the second effect is more dominant for the broad mega voltage beam in concrete. Okay. For the lead, pair production is a dominant type of interaction, and pair production doesn't give forward scatter secondary photon. Therefore, main effect along the beam axis is a beam hardening consequently. So that's why the TVL equivalent is less than the TVL1, is greater than the TVL1, sorry. Now we'll talk about the interaction coefficient. Photon may experience one or multiple interactions in the medium in which energy lost by the photon is converted into kinetic energy of electron. And this equation defines these losses. The kinetic energy of electron may be deposited in the medium through inelastic collision or removed from the medium through Bremsstrahlung. So what happens when photon interact and transfers energy on an electron atomic shell electron? So the electron will move forward or scattered. Maybe it get high energy, so it can produce secondary um, interaction with another atom, and it can produce further electrons. Or in some cases, it will close to the nucleus and it may produce Bremsstrahlung photons. So that G is basically is a Bremsstrahlung X-rays. Now the type of photon interaction. So these four types are usually considered. The coherent scattering is just a vibrational. It doesn't give energy to the orbital electron, whereas photoelectric effect, it transfers its all energy to the atomic shell and knock out the K shell electron. It produce and can produce characteristic X-rays and other reactions like Auger electrons. Whereas in a Compton scattering, the energy is quite high, and as compared to the orbital electron, and it usually interact with the free electron. The term free here means that the binding energy of the electron is much less than the energy of bombarding photon. So it will scattered, and there are equations for that, and we'll not going into the detail. The other is the pair production, where photon interact, and there is a certain energy threshold energy is required, 1.02 MeV, and it can produce electron and positron. And these are the coefficients of these equations. So what we learned from these variable affecting the interaction cross section. Linear attenuation coefficient defined by the tau for photoelectric, and this is for Compton effect and pair production. The mass attenuation coefficient.
Hello, sir.
These are the density. Yes.
Hello.
Yes.
Sir, I put it the question in chat box, sir.
Okay. How Auger electron produce? Okay, I will explain later this thing. Okay, in the end of the presentation, separately.
Okay, sir. Okay.
Okay. इलेक्ट्रॉन तो निकाल यारी के बगैर आपने कैसे होता अच्छा. Now you can see in this chart that photoelectric effect is dependent, highly dependent on the Z, that is density, atomic density, and the Z cube. Whereas the Compton effect is independent of this, and pair production is also depending on the Z. So dependence of energy is inversely proportional, whereas Compton effect decrease with the energy, and pair production is increase with energy. So now some concepts about the Compton scattering. Some important concepts, and I think you guys remember these equations, and you can put the values on these equations and you can find the results. The solutions are given in the Han books as well. So when the photon directly hit the electron, so electron travel forward, that is phi is equals to 0 degree, and the photon goes backward at 180 degree. So energy acquired by the electron is maximum, whereas the energy of scatter photon is minimum. The another concept is grazing hit. Electron emitted 90 degree. So photon interact with the like photon coming from here and interact with the electron, and electron goes 90 degree and photon move forward. So the energy is zero, no transfers of energy. By appropriate substitution, it can also be shown that energy transfer to the required electron is small at low and large at high energy photon energy. In designing the radiation barrier, 90-degree photon scatter is particular of interest. At high energy, photon is greater than energy of 90-degree scatter. So the energy is around 511 keV, that is 0.511 MeV. At 180-degree scatter is this. So what we are talking, okay, the question is, I think the characteristic X-rays can be produced the OJ electron. Yes, it could be. We'll talk about this later. Okay, and if you think about the LINAC, and just imagine that it is 90 degree, the radiation is emitting at the 90 degree, and at the other end, you talk about at the back of the gantry stand, there is a wall. So at that wall, what will be the energy? It's around 0.511 keV or 255 MeV. So those wall width can be reduced. So this is a concept of this concept helps in designing the radiation barrier. Okay, now let's talk about the importance of Compton effect, and this is a dominant effect in the radiotherapy, whereas a photoelectric effect is dominant in the kilovoltage electron. So it is the concept is important in radiology. Here you can see the density of the human body, fats, muscles, water, air, bones, and their number of electron per gram are quite similar. So the Compton mass attenuation coefficient is independent of atomic number. It depends on the number of electron per gram. Since electron per gram is constant for all the material except hydrogen, therefore is nearly the same for all the material. Compton coefficient. And this concept is defined in this graph. This is a Compton dominant region. Here you can see the water, it's same, and the lead. And this diagram is further explained with this. So in this level, you can see in this region, this mega voltage region, the water and the lead, this is a high dense material and this is a low dense material, is same. Where in the photoelectric region, you can see the characteristic X-rays, characteristic peaks are there. But when it reached the mega voltage region, the Compton effect dominant, and it's in the low material and the high dense material, it's same. Now we'll talk about the interaction of charged particle. The charged particle interact principally by ionization and excitation. Transfer of energy result due to the Coulomb interaction between the traveling particle and electron or atom. The Coulomb interaction with the electron result in ionization, excitation, whereas the Coulomb interaction with the nucleus result in Bremsstrahlung. Heavy charged particle can also cause nuclear reactions. So these are the graphical representations of the heavy charged particle interactions, and the heavy ions are also in use in radiotherapy. So this is a chart of neutron interaction. It interacts via two processes: recoil, collision like a billiard ball with transfer of energy to recoil atom, high interaction cross section with lighter nuclei, example hydrogen. Nuclear disintegration, neutrons enter the nucleus and disintegrate it to produce heavy charged particle and neutron and gamma rays. Electron interactions. So electron interaction is also important to understand because electron therapy is quite common in radiotherapy. In water or soft tissue, electron, like other charged particle, lost energy predominantly by ionization and excitation. This result in deposition of energy or absorb those in the medium. As electrons travel through a medium, they interact with atoms by a variety of processes owing to Coulomb's force interaction. The processes are inelastic collision with atomic electron, that is ionization and excitation, inelastic collision with the nuclei, that is Bremsstrahlung, and elastic collision with atomic electron, and elastic collision with the nuclei. So there are a number of interactions. Okay. Quantities of interest for charged particle: stopping power, rate of kinetic energy lost per unit path. Two type of electron interaction is collisional and radiative stopping powers. So LAT, kinetic energy transfer to the medium per unit path length, and LAT focus only on energy transfer through collision. LAT, linear energy transfer, is less than equal to stopping power. And this is a diagram to understand the collisional and radiative losses. And this is the last slide as well of my presentation. Okay, can you see my window? Can anybody tell me?
Yes, I see it.
Okay, this is a Hans book. So we're going to learn together about this chart. Okay. So the rate of energy loss depend on electron density of the medium. So we have two materials, water and lead. The rate of energy loss per centimeter square, which is called mass stopping power, is greater for the low atomic number Z material. So mass stopping power is greater. So you can see the water is greater as compared to lead. There are two reasons for the high Z material have fewer electron per gram than low Z material have. And the second, high Z material have more tightly bonded electrons, where water, of course, they are loosely bonded, which are not available for this type of interaction, as seen in a figure 14.1. The energy loss rate first decreases. So energy loss rate decreases and then increase with the energy of electron. So it increases a bit, minor increase in MEV region. But you can see in the MEV region, it's quite similar and up to the level of 10 MeV. No change for both the materials, with a minimum occurring about 1 MeV. Above the 1 MeV, the variation of energy is very gradual. The energy loss rate for energy 1 MeV is roughly 2 MeV per cm, and that's the rule of thumb we use in electron therapy. So the radiative losses. So radiative losses are high in lead as compared to water. The rate of energy loss per centimeter in a medium due to Bremsstrahlung is approximately proportional to the electron energy. So as high as the electron energy, the Bremsstrahlung losses are high. And yes, anybody want to ask anything?
Dear Asad,
Yes.
yes, I have a question, please. About linear energy transfer and stopping power. Isn't the same concepts?
I think it's different a little bit.
Because some books say that sometimes called linear energy transfer, it is the means stopping power, the same concept.
Allah, sorry, कौन आ गया भाई? Okay, I have to check this thing again. I'm not in position to answer right now. Okay, this is the end of my presentation. So anybody have any questions? Can ask. I try my level best to cover this topic, and I hope you guys have very good time with reviewing these chapters, and hopefully you all will join tomorrow for the lectures, and both the speakers are available. Mohammad Ali Shah Saab will talk about the Linux, basics of Linux, and he's from America. And